Okay, let me start from this slide. Last two lectures, we went through all the details about the in-filter interaction with converter controlled by voltage mode control. And we took one specific example, which was boost converter. And we studied everything using the boost converter. The reason using the boost converter is it shows the impact of in-filter interaction very clearly and interestingly. And when the voltage mode control is concerned, all the three PWM converters are the same in terms of the shape and pattern and output of in-filter interaction. So we go step forward to the current mode control. As I said previously, maybe I said more than one time, maybe more than twice, the pattern of in-filter interaction is very different depending on the converter topologies. In this case, boost converter and buck boost converter, they show almost the same features, but the case of buck converter is utterly different from the other cases. So first, we take the look at this boost converter with current mode control. Again, input filter is inserted here. This is uncoupled boost converter combined with in-filter. So this is in-filter coupled boost converter with current mode control. Okay, this is operational condition: input voltage and input current, out voltage and out current, and this is the switching frequency and CSN gain, DC gain of current sensing network, and this is the compensation ramp slope. Okay, so we studied all the details about this in the previous semester. This is the voltage feedback compensation employed to that converter. This is a two-pole 1-0 structure. This is the optimal, or only one structure desired for this current mode control for PWM converters. And the pattern of input impedance of this converter, boost converter with current mode control, is way different from the previous case. This is the prediction of asymptote of four different input impedances: GIU, GI prime, double prime, triple prime. They are the magnitude asymptote, and these are the phase asymptote. First, take a look at this magnitude plot first, okay, and just forget about this one for the time being. And there are four input impedances, but they are divided into two groups. This is regular input impedance of converter with current mode control. This is output nullified input impedance of converter, GI double prime, and this is closed loop controlled input impedance. Again, this is also closed loop controlled input impedance. So you are seeing two different types of closed loop input impedance of converter. So there are this GIU and GI double prime. So these are closed loop GI. Okay, I use just the GI. Okay, and the other two are, this is the open loop input impedance with output shielded. So this single prime is open loop impedance, and the triple prime is simply open loop input impedance of the converter. So they two of the impedance merged together, and the other two combines here, right? So this is the typical structure of input impedances. And comparing with the voltage mode case, for the voltage mode control case, GI triple prime was something like this, and the GI prime, just the GI prime was something. Not this one. Oh, I'm sorry, not this one. I need to go down further. Okay, so Right? This is the case of voltage mode control of GI triple prime, and the GI prime for the voltage mode control was something like this. GI prime was something like this. This is the case of voltage mode control. And current mode control is, in current mode control, this magnitude of two impedances at this frequency range is boosted this much, so much, right? What makes the difference? This is a closed loop controlled input impedances, right? But this is open loop input impedances, right? So open loop impedance means impedance is evaluated with this voltage loop opened, right? For the voltage mode control, there is only one loop, feedback loop, which is voltage loop. If voltage loop is open, then whole system becomes open loop system. But situation is different. This is the case for the current mode control, and these two impedances are evaluated with voltage loop open, but current loop is still closed, right? So this is the effect of the current loop, internal current loop embedded in current mode control. Okay, let me repeat this. For the voltage mode control, if you open the voltage loop, all the feedbacks are gone. Okay, so they are really open loop input impedances, which is shown here, GI triple prime and the GI just prime. Okay, but for the case of current mode control, you open the voltage feedback loop, but still the internal current loop with current mode control is closed. So it's not really open loop impedance. It is partially closed impedance. Okay. So then that current loop, internal current loop of current mode control boost the impedance of these two guys this much during this frequency range. Okay. So that make difference. Right? So this is the benefit of current mode control coming from the internal current control embedded in current mode control. Right? So that result is shown here. Okay. And let's take a look at this phase characteristics for these two guys, GIU and GI prime. At low frequencies, it has minus 180 degree phase characteristic. So it behaves as the negative incremental resistance at these low frequencies. But if you take a look at this open loop impedances, the phase is around the 0 degree. So it behaves as a regular resistance. So if you have overlap, suppose output impedance of this filter, in filter overlaps something like this, this is very dangerous. This is the unstable overlap, right? But this overlap is okay, non-fatal overlap. But suppose your output impedance of your infilter overlap with this, then this output impedance must overlap this thing also, right? So overlapping anything, any impedance here, result in instability, right? So to maintain stability, output impedance of the infilter must stay below this line, okay? That is the requirement. But if you obey that rule, the maximum of the output impedance of your infilter falls below this line, then everything is fine. Okay, no stability problem, and there is no overlap. Okay, so this actually current mode control eases the problem of infilter inaction. Okay, so this is theoretical prediction. Blue one is analytical prediction, and the black ones are the computational method, so they are very close, right? So this result is very accurate, and this is the result of the one of my paper. So in that paper, I analyzed everything for input impedances for 3 PWM converters with 2 different control scheme. So it is what 2 times 2 times 3, 12 different input impedances. That was quite a job, very tedious job. Okay, it requires some energy and something. And my student, actually I first derived this maybe 20 years ago, and my student, they derived this for the general cases. For the first paper, I used the resistive load, and in the second paper, the final paper, my student used the condition of uncoupled converter, which provide more general result. Okay, this is the result for the uncoupled converter, right? And I'll introduce that paper at the end of this chapter. So that paper is very useful, but very tedious. And usually people, they don't buy it, okay? So they are saying why this analysis is unnecessary, something like that. You did a job, but that job will be useless, something like that, okay? Again, Chinese guys, right? Then the prediction, this low frequency asymptote, is this. This is the negative incremental resistance given by ratio between the DC value of the input voltage and DC current of input port, which is this. So it matches with this number. And this one is what? This one is much, much larger than this, all right? That means there are substantial distance between these two curves and these two curves. That is the benefit of current mode control, okay? This is the summary of the previous analysis or previous observation, okay? So the GI prime and the GI triple prime are well damped and by internal current feedback. I need current here. Current feedback mechanism embedded in the current mode control. Okay? So at low frequencies, GI prime and the GI triple prime are substantially increased so that there is a relationship of this one. So GIU and the GI double prime, they merge together at low values, and the other one merges together at much higher values. So we have this huge difference, okay? And this GIU, closed loop input impedance, behaves as negative incremental resistance of this value at wider frequency range, starting from DC to this part, okay? So this is the result of the input impedance analysis. And let's take examples. I generated this case. I design in filter. I selected the parameters to generate this output impedance of this in filter. This is GOF0, which is this one. GOF0, okay? So it stays below this value, but they are very close, okay? I intentionally selected this. If I select something this one, the analysis will be trivial. There is practically no impact coming from the in filter, okay? But I selected this to address the nearness of these curves, okay? For this case, this peak value, this output impedance of in filter are well separated from this open loop input impedances, but they are very close to this closed loop input impedance. So I'd like to show the impact of this nearness of these impedances. Okay? So parameter. So here, this is a parameter I selected to generate this, and this barely meet the stability requirement for the stability of the combined converter. The peak value falls below this line, so it is below this line, but they are very close. It is nearing to this line, so maybe you can expect that this converter may remain stable, but very poor in closed loop performance. So in filter inaction will be pronounced a lot because of the nearness of this. Okay, but even with this condition, there is a sufficient distance between these two curves and this output impedance. Okay, so the performance criteria determined by ratio of this and something won't be changed. But performance criteria related with these values will be changed a lot. Okay. So, and the phase characteristics of these two closed loop input impedance has minus 1 8 degree, and the phase of this one, this output impedance of this in filter at this frequency range is what? Is 0. Okay. So this region, the phase is plus 90, and this region is phase is minus 90, and this part, okay, this top at the top frequency, phase gotta be 0 degree. Okay. So if they come close together, there is something will happen. So I'd like to show that. Okay, so this is the analysis of audio susceptibility for the previous case. I repeated. Okay, this is the analysis of audio susceptibility for the previous case. So I repeated the plot of input impedances and the output impedance of in-filter in this frequency range. They are merging together, almost merging together. Okay, so under this situation, this audio susceptibility is expressed like this. This is the same equation we used in the previous analysis of voltage mode control. Okay, but in here, this condition is apparent. Okay, so because GOF0 is somewhere here, and this one, these two plus are way above this value, so always we have this condition. Okay, so this condition should be satisfied, because for the stability, peak value of this output impedance of in-filter should stay below this one. There is a huge difference. So this inequality is valid always. Okay, so anyway, this is the expression, and we need to take a look at this. Right? So this one, this ratio of this GOF0 and the GIU, okay, they are coming together at this frequency with about the same magnitude. They are approaching in magnitude, means the magnitude of two curves becomes same, but phase is 180 degrees apart. They are out of phase. Okay, so sum of this, one and this one becomes what? It approach minus 1, right? Magnitude is 1 and the phase is minus 180 degrees. Then means this becomes minus 1. So then 1 plus 1 minus 1 approach 0. Okay, so this becomes 0. Whole denominator goes to 0. Then this term goes to infinity. Right? So with this situation, we are expecting huge peaking in audio susceptibility at this frequency, at this nearing magnitude nearing frequency. That analysis is shown here. This is the audio susceptibility of uncoupled converter, and this curve is this one. This factor 1 plus GOF0 divided by GIU. Magnitude of them is shown here. So this term shows this dipping, sharp dipping, right? This term is coming in the denominator. It comes in the downstairs. So it generates peak like this. So this one is audio susceptibility of in-filter coupled converter. So it shows this peaking, right? So you are seeing peaking here. Okay. So what is the problem with this peaking? This peaking will generate some very oscillatory behavior in the transient response. For the case of step input response, if you simulate or evaluate step input response, this will be converted into underdamped oscillation, will produce the oscillation at the frequency of this peaking. Right? That is one case. And another one is if there is some noise falling in this frequency range, then noise, sinusoidal noise, will be amplified. Right? You are expecting some attenuation of the sinusoidal noise for the older frequencies with this infilter function, but actually, and at this particular frequency, the sinusoidal noise will be amplified this much. Right? So this is a problem, and it also indicates the converter is on the verge of instability because the huge peaking always means very small phase margin. That means converter is almost unstable. Okay, so that is shown in the audio susceptibility analysis. Okay, let's take a look at the output impedance case. This is the expression for the output impedance of in-filter coupled converter. This is the output impedance of uncoupled converter. So we have two terms here, right? But this one is very small, right? So GI prime is much larger than GOF0. We know from this result, this input impedance comparison. So this term can be ignored. Right? Then remaining equation is this. This is very simple equation, but if this becomes approach the unity at this frequency range, magnitude of this GOF 0 and the GIU becomes almost same. Okay, but with the phase is 100 degree apart, 180 degree apart, out of phase. Then this reduced to -1, and this term goes to the 0. Then this part will generate peak. Okay, same as the previous case. So you are seeing this peaking here, right? So this is output impedance of uncoupled converter is shown here. This part, okay, and this part is this factor, multiplication factor of this. No, this one, okay. Then this term coming in the denominator, so it generates a huge peak like this, all right? So it has the same consequences. This will produce some oscillation for the step load case because this is the output impedance, right? Then transient response from the step load current change to output impedance will be very oscillatory. It will generate slightly damped oscillation at the frequency of this peaking, which is the frequency of this one. Okay, so this is again this indicate this converter is almost unstable. It is stable, but stability margin is very small. Can be seen here. Take a look at the loop gain. The expression of loop gain is shown here. Loop gain of source coupled converter, in-filter coupled converter, and the loop gain of uncoupled converter. And we have two multiplication terms. Okay, one is this, and this. The other one is this, and this GI triple prime is much larger than this, so this can be ignored. Then you have this. This can be ignored. Then you have this. Okay, multiplication of two terms. This is the sum of two terms in log scale. And again, with this, at this frequency range, magnitude becomes unity and the phase becomes -180. They are out of phase. So it becomes very small, but this time, this term is coming in the upstairs. So we are seeing what? Dip in the loop gain. So dip occurs here. Right? So this is very dangerous. Okay. Of course, the previous analysis is saying that the converter is on the verge of instability, but in this case, this directly shows the phase margin is running out. Phase margin should be measured, should be evaluated at the loop gain crossover frequency. At this point, so let me draw the vertical line here. Then phase is maybe larger than -180, but margin will be very small. Phase margin is diminishing. it depends the way of drawing this vertical line. So maybe it has very small phase margin. Okay, so this converter is stable. The performance will be severely degraded by this in-filter interaction. This problem happens many times for the boost and buck boost converter. So you need to take a look at this impedance input impedance comparison curve with this output impedance of load subsystem. Okay, if you blindly design this will go like this. Okay, maybe the peak value of this output impedance stays below this line. You are okay. It is stable. The closure performance of becomes unacceptable for the most practical case. Okay, so this kind of information is only available through this in-filter interaction analysis. Let's take a look at the step load response of this converter. This is output impedance characteristic of in-filter coupled boost converter with current mode control. Okay. As we went through, this output impedance of this converter has this huge peak at this frequency. This frequency is the impedance approaching frequency, right? So, and this is the time domain simulation of step load response of this converter. So, load current was initially 4 amp, it went down to 2 amp and went back to 4 amp. The response is shown here. It is the case of uncoupled converter. Okay? So this is the best transient response you can obtain. Okay? So this uncoupled converter is optimally designed for the best closure performance, and you connect the in-filter. In-filter does not destabilize the converter, but it considerably degrades the closure performance. This is the response of this converter with the same step load changes. So it generates this oscillation. Again, it generates this oscillation. This oscillation is closely related with this shape of this output impedance. In general, if you use the peaking, you should expect the oscillation at this frequency, and this degree of oscillatory behavior is somehow related with this peaking, and this is related with phase margin of loop gain. You know the expression of this. Right? The phase margin of this converter, maybe we use, this one. Okay, this is phase margin. Then peak is 20 log cosine PM phase margin. The time phase margin. We derive this equation? Probably not. Okay, so we'll be deriving this later, or maybe I think we already derived this in the previous semester. This is the exact expression. So there is a relationship between this peak magnitude of peaking and phase margin of loop gain of this converter, and this will be very small with this huge peaking. Then this small phase margin translated to the oscillatory behavior of this converter, and the frequency of oscillation TOS is 1 divided by this frequency, this peak frequency. So this number provides us about 2 millisecond oscillation period. So let's take a look at this. The oscillation frequency, we take this peak point here and another peak point here. Then distance between two peak points is near 2 milliseconds. Okay, I'm not quite sure. Okay, but it will be very similar to our theoretical prediction. This small division is this division 3 milliseconds. Okay, so maybe this is slightly larger than 2 milliseconds. Okay, but our prediction is 2 milliseconds. They are very close. Right? All right. So this is about the case of boost converter with color mode control. Okay, let's summarize our analysis. This shows the typical shape of input impedance of this boost converter and output impedance of in-filter, right? Previously, this was approaching near this, so the converter had some problem. But to avoid that situation, we need to have sufficient distance here, all right? That is the case here, okay? So this requirement, conservative requirement, this is the requirement, safe requirement to maintain stability. So the conservative requirement is to provide sufficient distance between them. If you provide only small distance, you will be seeing the performance degradation and very oscillatory transient behavior with very small phase margin of the loop gain. Okay, so that is the first case. And if you satisfy this is the conservative stability requirement is satisfied, then distance between this and this is larger than previous case, larger than this case. So this meets all the requirement for the minimal in-filter interaction. With this kind of condition, you won't see any impact of in-filter on the closed loop performance of your converter. Okay? So this is the desired situation. If you meet this condition, then your converter remains the same as the case of uncoupled condition. That is, again, there is the benefit of color mode control. So color mode control improves the in-filter interaction property of this converter. So again, there is the one benefit of color mode control. Okay, maybe it is interesting to compare this case with voltage mode control case, which is shown here. Okay, let me address this. In this case, for the color mode control, there are two feedback loops, right? For this case, both current loop and voltage loop are closed, right? In here, this voltage loop is open because this is defined on the condition of voltage loop open, but still current loop is closed. So current loop is providing the boosting of impedance. Okay, without current loop, this guy will be something similar to this. One will be like this. They are boosted this much. Okay, so it compares with this case of voltage mode control. All right. So voltage mode control. For this case, GI double prime and the GIU, they are closed loop input impedances. So voltage loop is closed, but this is the open loop input impedances. Feedback loop is open. The only one feedback loop, which is voltage loop, is open. So open loop characteristic is directly transferred, delivered to these characteristics. So we have this dipping here, another dipping here. This is the problem of voltage mode control. So by maintaining this peak value of output impedance filter well below this line, you secure stability of converter, but closed loop performance will be affected by overlap of between this output impedance and this open loop impedances, two of them. Right? We have seen the problem of this feature in the previous lectures. Okay, so this is the basic difference between the voltage mode control and current mode control. For the case of buck boost converter, all the situation is very similar to the case of boost converter. So we don't need a separate analysis. Okay. However, the buck converter shows very strange behavior at the presence of in-filter interaction. We'll discuss this in the next lecture, and we will draw some final conclusions about the in-filter interaction in three basic converters with current mode control or voltage mode control.